is going to be the change in the magnetic field is going to induce the electric field. Okay? That is the third Maxwell equation. Now, fourth Maxwell equation is change in electric field induces magnetic field. Okay, so what you're going to do is to do the same thing on here. The electric constant or around T around electric field plus 4 pi sigma of the electric field. You can notice that there is a conductivity here. The sigma is conductivity. Conductivity of the material. So change in the electric field has something to do with the conductivity of the material itself. So actually this part is kind of a damping factor of the whole system, right? So conductivity has to be included in the Maxwell fourth equation, something like that, right? Now, how can you get use this Maxwell equations to get the light wave equations? Now, just before doing that, let's cover the one thing first: dielectric, electric relaxation time. Relaxation time. Dielectric relaxation time. Now, from Maxwell fourth equation, we know the curl of magnetic field is related to the change in electric field and the conductivity of the materials, right? That's the fourth equation there. And in the mathematics, we know that this formula, it has to be 0. So what you're going to do is we just apply the Laplacian on here, not the Laplacian. We're going to do the dot on here, and then the right-hand side is going to be 0, and then we're going to put the derivative, okay? Then what we end up with is round T electric field and the 4 pi sigma over C electric field, something like this. We just apply the dot on here, okay? And then first Maxwell equation, the first Maxwell equations. We know that electric field can be isolated to get the charge density like that, that is the first Maxwell equation, we have this thing this thing can be equated with using this Maxwell first equation. Then we end up with round t over round rho over round t plus 4 pi sigma over epsilon r, charge density is 0. Okay? And that's a simple first order differential equation. And it's not difficult to get the answers to that, which is charge density now is going to be initial, and then decay factor is going to be T over tau R, where the tau R is going to be dielectric constant over 4 pi sigma. It looks very natural, but we can get these numbers in a mathematical formula like that using the Maxwell equations. And typically, I'll give you the typical numbers for this. Dielectric constant is 10, and tau R, relaxation time, is 10 to minus 12 per rho sec. Okay? And sigma is 10 to the minus 16 per ohm centimeter for insulator, and 10 to the 6 ohm centimeter for metal. So you can put these numbers to get the dielectric relaxation time, tau R, for this, and then you can get the dielectric relaxation time. And you can see that if you put these numbers to this, then maybe you can see in the insulator case, dielectric relaxation time, insulator case, dielectric relaxation time is around 1,000 seconds. They're pretty long, isn't it? And in a metal semiconductor case, semiconductor, it's about 10 to the minus 12 sec. And metal, 10 to minus 17 sec. What is the use for the dielectric relaxation time? The copy machines, they should have a long dielectric relaxation time to copy any materials, okay? So it has to use the insulator for this copy machine. Dielectric relaxation time in physical sense, it's nothing but when you have a solid like here, when you insert the charges to this material locally, and then dielectric relaxation time is nothing but a time necessary to spread out into these materials. That is the dielectric relaxation time, right? And if in case of an insulator, the dielectric relaxation time is 1,000 seconds. It means that for 1,000 seconds, these charges, if you inject that into the material, it stays there before it's spreading out, right? So that's how we can use the jerks insulators for the jerks machine. Now, the things that we're going to discuss is how the electromagnetic wave, okay, how the electromagnetic wave, how can you get the electromagnetic wave out of this Maxwell equations? And you start out the formula like car something should be related to the Laplacian and dot product minus square electric something. Okay. That is a mathematical formula. So what you're going to do is you're going to use this Maxwell fourth equations. You apply curl on this, okay, at fourth equation. Then you are going to get something like this. Mu r of c round t round h. Then that is going to be equal to 4 pi rho over the electric constant and minus del minus del square electric field. Okay? And this is equal to the you can manipulate this equations to this form, 4 pi over the electric constant rho minus electric field and you put this thing on the fourth equations. Then minus 4 pi over 4 pi mu r conductivity and c square round t round electric field should be equal to 4 pi over the electric constant rho minus electric field, something like this. And here, this is at steady state. Steady state means no localized charge, so that that rho should be 0. So at steady state, the equation that we have manipulate according to the Maxwell equation is going to be something like this. Square electric field, mu r, dielectric constant, c square, round t square, round square, electric field, plus 4 pi mu r sigma over c square. That is the light velocity in a vacuum around t, around this electric field. It looks complicated, but it just follows what the wave equation should look like, right? One is the spatial derivative, and then this is the time derivative. The only thing is, this is we have this damping factor. Damping factor. And let's see. We can do the same thing for the magnetic field. So if you apply that to the magnetic field, then you end up with some equations round t square round square h plus 4 pi mu r sigma c square round t over round h. It's going to look like this. You do the same thing on the magnetic field. Now, in analyzing these equations, light equations, let's have the cases where the insulator case, insulator, if the material is an insulator, okay, which means that the conductivity is 0, then this part disappears, so that the equation becomes a simple something like this: mu r e r over c square round t square round square over e, something like this, right? So this is the typical wave equations. Wave equation, right? Then the solution of this is going to E naught e to the I k r minus omega t. It should look something like this, right? That is the general solutions. And here the velocity, which is dispersion relation, the slope in the dispersion relation, is going to ER mu r. And this is the velocity of the light in the dielectric constant and permittivity of the material. So this is a constant values, which means this is a non-dispersive system. Non-dispersive system. Dispersive system. So as far as the material is an insulator, so the conductivity is 0, then the light wave in that material is going to be non-dispersive system. Non-dispersive. Index of refraction. Index of refraction. By definition, that is the velocity ratio in the medium, and then that is going to be ER mu R, and that is going to be dielectric constant because permittivity is 1 in most of the materials at optical range, optical frequencies. Now, what happens if we have the conductivity is not 0? So it's a conductor. Sigma is not equal to 0 case. Okay, then we have to use the whole equations. And we're going to define a R star as a complex number C star over V complex velocities, and then that is going to be the real number, and it should consist of these two things, right? And we can see that this complex index of refraction is separated the real and imaginary values, where in this case the imaginary value gamma is absorption index. We call this absorption index. Okay, then R square is nothing but R square minus gamma square plus I to R gamma. So if you equate these two things together, then you see the dielectric constant is going to be R square minus gamma square, okay? And then the gamma is 2 pi sigma over omega R. R is square root of gamma square, and R is also 4 pi square sigma square over R square omega square.